Okay, we're going to talk about the ladder problem. So let's imagine we have a ground and we have a wall, and we put the ladder up against the wall, and we want to talk about the forces that are acting on the ladder. Well, clearly the ground pushes up on the ladder, and I'm going to call that N1. And the earth pulls down on the ladder, and I'm going to call that W, and I've chosen it to be halfway up the ladder because that's where the center of mass of the ladder is. The wall is going to push against the ladder, and I'm going to call that N2. I'm actually going to try to do that in red so that we can distinguish those. And then the other force is the force of friction on the ground, force of friction between the ladder and the ground. And now what we're going to do is sum of the torques. And remember, sum of the torques looks like the sum of R cross F, or the sum of R perpendicular to F. So I'm going to actually say, let's do the torque associated with the weight. Well, I want to know what the component of L that is perpendicular to W is. So if that angle is theta, then that's going to look like L over 2 times W times the cosine of the angle. And I'm going to make that negative because it's going to have a tendency to make the ladder rotate clockwise. The torque associated with N1 is equal to 0 because in this case L is equal to 0. I'm assuming, and that was not clear, that I'm pivoting about the base. I'm now going to look at the torque associated with N2, which is equal to, I'm going to write that as N2, and then I want the component of L or R that is perpendicular, and that's going to look like L sine theta. Remember, we're going to take and put that one in green. That was this component right here, the L over 2 cosine theta. And 2 is going to be L sine theta, because again, it's just the perpendicular component of the force, or the perpendicular component of the radius vector in this case. Now I'm free to add up the torques. I can actually add in one more. Sum of the friction force, that equals 0 because again L equals 0. And now I can do sum of the torques, and what I have is minus L over 2 W cosine theta plus L N2 sine theta. And then the other equations I have to write are sum of the forces in the x direction, which is going to be force of friction minus N2, and then sum of the forces in the y direction, which are going to be N1 minus W. You're going to recall that friction is mu N1, so I can write, and these are all going to equal 0, so 0 is equal to mu N1 minus N2. And now I have enough information that I can solve for my equations. This is also equal to 0, so N1 is equal to W, and I can plug that into here, and I get mu W is equal to N2. So this equation and this equation will allow me to solve for the minimum friction. But the important piece is when I look at a force, so the W force was in that direction, and I looked for the component of, in this case, the radius that was perpendicular to the W, and then for the force that the wall pushed off against, I said I'm going to look at the L or the R that is perpendicular to N2.